Hello everyone, my name is Aditya Raj Rajat and my registration number is URK23CS1010. Today we'll be looking at experiment 5, building a multi-layer perceptron using PyTorch, and this is a step up from our single layer perceptron. We are now building a deep neural network with multiple hidden layers, and we'll be working with the breast cancer dataset, classifying tumors as malignant or benign using 30 different features. And we're using PyTorch, which is one of the most popular deep learning frameworks out there. So, what's a multi-layer perceptron? Think of it as stacking multiple layers or no, multiple single-layer perceptrons together. We have an input layer, multiple hidden layers, and an output layer. Each layer learns increasingly complex patterns. Uh, and the breast cancer dataset is perfect for this. It's not linearly separable. So so we need those hidden layers to capture the complex relationship between features. So let's start with question one. Loading the dataset. We are using the sklearn's built-in breast cancer dataset. This is a classic dataset for binary classification. Let me show you what we are working with. So 30 features describing characteristics of cell nuclei, things like radius, texture, perimeter, area, smoothness, and so on. And yeah, question two is straightforward. We assign X as all features and Y as the target. Nothing, it's just quite basic. We are just setting up our data. So question three is basically about standardization. This is absolutely critical for neural networks. So I used a sklearn standard scaler to transform all features to have mean 0 and standard deviation 1. So you can have a look at the before and after. Originally, features and originally features had different scales, some ranging from 0 to 10, others from 100 to 1000. After standardization, they are all comparable. So moving on to question 4, train test split. So this is where we assign 80% for training and 20% for testing, and I use random state is equal to 42 for reproducibility. You can see we have 455 training samples and 114 testing samples with similar class distributions in both. So question 5 is basically converting to PyTorch tensors. This is where we move from NumPy arrays to PyTorch's tensor format. Tensors are like NumPy arrays but optimized for GPU operations and automatic differentiation. So I convert X and Y to float 32 tensors, reshape Y to the correct dimensions, and create data loaders with batch size 32. And moving on to question 6. Question 6 is where we design our neural network. So I define a class MLP that inherits from the NN module. That's PyTorch's base class for all neural networks. And in the constructor, I define our layers. So layer 1 is basically linear from 30 inputs to 64 neurons. Layer 2 is linear from 64 to 32. Layer 3 is linear from 32 to 16 neurons. Layer 4 is linear from 16 to 8 neurons. And the output is linear from 8 to 1 neuron. I also define activation functions. Uh, so as you can see, uh, in the forward method, I define how data flows through the network. Input goes through layer 1, then ReLU, then layer 2, ReLU, then layer 3, then again ReLU, then layer 4, ReLU, and final output with sigmoid. Then moving on to question 7, training. This is the most, this is where the training happens. And first, I define our loss function. Binary cross entropy loss, which is standard for binary classification, and our optimizer Adam with learning rate 0.001. Adam is adaptive and usually works well without much tuning. So then we train for 100 epochs. In each epoch, training phase happens, and where we set our model, where we set model.train and loop through batches. And then comes the testing phase. We set model.eval, and evaluate on test set. This gives us test loss and accuracy. And I print progress every 10 epochs. Watch how training loss decreases and accuracy increases. So we go to question 8. First, training and test loss over. Question 8 is basically about plotting training curves. So I create three plots. First is the training and test loss over epochs. Both should decrease smoothly. And second is training and test accuracy over epochs. Accuracy should increase and plateau. And third is loss versus accuracy. This shows the trade-off. As loss decreases, accuracy increases, which is exactly what we want. Then moving on to question 9, testing. So here I run the model on a test set and collect all predictions. Then I show the first 30 predictions with actual versus predicted. So most are correct. You can see the check marks. Overall test accuracy is calculated. Then question 10 is a comprehensive evaluation. I use sklearn's metrics function since we are just evaluating, not building the model. So first comes, first is the confusion matrix. So let me explain what these numbers mean. So true negatives are correctly predicted. False positives are predicted benign but actually malignant. Uh, True negatives is correctly predicted malignant. Right? So false positives are predicted benign but actually malignant, and that's dangerous. So then false negatives are predicted malignant but actually benign. That's also bad. And true positives means it correctly predicted benign. So you know I also calculate specificity, true negative rate, and follow, which is a false positive rate. And you can have a look at the metrics. So, and I've also created multiple visualizations, such as a confusion matrix, heat map matrix, bar chart, pie chart, and so on. And first, the key insights from this is first, deeper networks can learn more complex patterns, and our MLP significantly outperforms what a single layer perceptron could do on this data set. And secondly, PyTorch makes everything easier with automatic differentiation. We don't have to manually compute gradients like in experimental, for with a single layer perceptron. So third is proper evaluation is crucial. Accuracy alone is not enough, especially for imbalanced data sets. Precision and recall tell us more about real world performance. So that's it for this experiment. Thank you.